find the area of xy dx, where r is nothing but the region bounded by the coordinate axis and the line x plus y is equal to 1. Now the coordinate axis, this is y is equal to 0 and this is x is equals to 0, and the line x plus y is equals to 1. Now we have to find this region. Now clearly x is varying from 0 to 1 and also y is varying from 0 to 1. Now the given integral is nothing but double integral over r xy dx dy. If I consider x as 0, it is varying from 0 to 1. Now if I consider y as 0, it will vary from 0 to 1 minus x, which is xy dy dx, which can be written as x is equals to 0 to 1, y is equals to 0 to 1 minus x, xy dx dy. If I integrate, it will be x is equal to 0 to 1. If I integrate y, it is y square by 2 between the integrals and x. So this is nothing but integral x is equals to 0 to 1 x by 2. I'll take this half out of the integral, half into x into 1 minus x whole square dx, which can be written as half into x is equals to 0 to 1 x minus 2x square plus x cube. If I expand this and simplify, then the integration is nothing but half into x square by 2 minus 2x cube by 3 plus x power 4 by 4 between the limits 0 and 1. If I substitute the limits, value will be 1 by 24, which is option B. That in a factory, on an average 20% of the bolts produced are defective. If 10 bolts are selected at random from a certain on a certain day from this machine, then he is asking what will be the probability that 2 or more bolts will be defective. Now probability of defective is given as 20%, which is nothing but 1 by 5. So the probability of non-defective will be 4 by 5, and we have to find the probability of 2 or more bolts defective. So that means it could be 2, 3, 4, so on up to 10. So instead of finding 2, 3, 4, so on up to 10, it is enough to find 1 minus probability of no bolts defective minus probability of 1 bolt defective. We'll use binomial expansion to solve this problem. So 1 minus, so we are selecting out of 10 bolts, so the value of n is 10c, and we are selecting 0 here because no bolts are defective, and 0.2 to the power of 0 into 0.8 power 10 minus, similarly for 1 bolt 10c1, 0.2 to the power of 1 into 0.8 to the power of 9. If we simplify, the value will come up to 0.6242, which is nothing but option D.
For a circular shaft subjected to twisting moment, the maximum shear stress will be at. Here the options are A, C only, B and C only, B, C and D. Here it is a circular shaft which is subjected to a twisting moment. That means the shear stress is induced in the circular shaft. So it is a pure shear case. So generally in case of pure torsion, the shear stress is directly proportional to the radius of the circular shaft. So here if you consider a circular cross section, generally the shear stress varies proportionate to the radius of the shaft. So here is the maximum shear stress induced in the member, and at the center, so there is no shear stress, that is shear stress is 0. So that means the maximum shear stress occurs at the surface of the shaft. So at any point on the surface, the maximum shear stress is maximum. So in the given problem, here are the options B, C and D. So these are the 3 points where the maximum shear stress is induced in the member. So here the correct option is D. D is the right answer. Washing machine as shown in the figure consists of a rotating drum containing the washing inside a non-rotating cylinder tub. The whole assembly complete with ballast masses to increase the mass, and wet washing has a mass of 40 kg. It is supported within the casing on an arrangement of springs and dampers so that its damped natural frequency for vertical motion is 5 Hz, and the linear viscous damping coefficient is 0.2. The design spin speed Sorry, here the linear viscous damping coefficient is zero point 0.2. The design spin speed is 1200 rpm. It is estimated that the maximum likely unbalance due to the wet washing is zero point 0.2 kg meter. At the design speed of 1200 rpm, find the vertical force that would have been transmitted to the casing if the tub and drum assemble had been rigidly attached to it. So here the given diagram. So coming to the solution. So here the tub and drum rigidly fixed to the casing, so that the maximum balance force transmitted to the casing would be here mr omega square. Here mr omega square, where omega is 2 pi and 60, 2 pi n by 60, that is where n is the speed, design speed. So that is 2 pi into 1200 by 60. And coming to the, let us say this is equal to 40 pi, and mr is given as the most likely unbalanced force is 0.2 kg meter, and is equal to mr is equal to 0.2 kg meter. So that the total unbalanced force would have been transmitted to the casing is equal to mr omega square, that is 40 pi square into zero point 0.2, so which is equal to 3158 newton. So here the right answer is 3158 newton, and in the options the correct option is C the right answer. With a mass of 30 kg has a radius of gyration of 2 meter. Find the energy stored in the flywheel when its speed increases from 202 rpm to 250 rpm. Here the options are 3.57 kilojoules, 7.14, 14.28 and 57.12. So coming to the energy stored in the flywheel, actually here the flywheel speed increases from 202 rpm to 250 rpm. That is, the increased energy stored in the flywheel is equal to, let us say, E is equal to 5 half I into omega n square minus omega 2 square, where I is equal mk square, mass moment of inertia, where m is 30 kgs and k is radius of gyration, that is 2 square. Here it is 120 kg meter square, and omega 1 is equal, let us say this is the final speed, that is 2 pi into 250 by 60, which is equal to 26.18 radians per second, and omega 2 is given by 2 pi into 202 by 60, so which is equal to 21.15 radians per second. And the energy increased in the flywheel, or energy stored in the flywheel due to the increasing speed of 202 to 250, is equal to half into 120 into 26.18 square minus 21.15 square, is equal to 14.28 kilojoules. So the, the right answer is 14.28, and in the option the correct option is C. C the right answer.